Hello everyone. This session we are going to discuss on the topic properties of polymers. The main mechanism of drug release or how the polymers can control the release of the drug etc. we have discussed in our previous classes. First let us see what are the ideal characteristics of a polymer. Because the polymer plays a main and major important role in the development of drug delivery systems. And these drug delivery systems either we are administering to our body orally, or this polymers has been inserted into the body cavities or been inserted in the form of an implant in our body. Thus, this polymers goes into a biological system. It should have certain characteristics of certain ideal properties for this polymers so that it should not be harmful for our body. Considering the safety of the biological system, the ideal characteristics of the polymers has been identified as: first one, it should be compatible with the biological environment. It should not be non-toxic or it should not be non-antigenic. Second thing, it should be easily administered. We could able to administer very easily. It should be biodegradable or be eliminated from the body after its function is over. Biodegradable. That means it could be able to degrade by our body itself. Should be easy and inexpensive to fabricate. Should not be too costly. Should provide drug attachment and release site for drug polymer linkages. So these are some of the characteristics of an ideal polymer. Now let us look into the properties of polymers. Polymers displays different thermal, physical, mechanical properties depending on the structure, molecular weight, linearity, intra and intermolecular interactions. So the polymers can exhibit thermal, physical as well as mechanical properties. So all these properties we are not discussing here. Some few properties which we may commonly discussed in our pharmaceutical polymers we may be discussing here. So among these physical, thermal and mechanical properties, the reason for exhibiting such properties is because polymer to polymer there is variation in the linearity in the chain structure of the polymers, molecular weight as well as the intramolecular interactions and viscosity etc. So these are some of the factors that can exhibit or that helps to exhibit different mechanical or different properties for the polymers. The properties has been classified or been enumerated as thermodynamic properties, which includes the glass transition temperature, melting point, then rate of hydration, solubility, crystallinity, heat of fusion, versatility, molecular weight, biocompatibility, viscosity and thermal stability. So these are few properties of the polymers. Let us see one by one. The first one, the glass transition temperature. It is the temperature range where the polymer change from a rigid glassy material to soft material and is usually measured in terms of the stiffness or modulus. So this is the temperature, or which can be explained as the range of the temperature, say 150 to 175. The range of the temperature at which the rigid polymer is not melting, the rigid polymer becomes soft. So the temperature at which the temperature at which the transition of the polymer happens, the range of the temperature at which the transition in the state of the polymer happens from rigid to soft. So this is we considered as the glass transition temperature. Second thing is melting point. You know very well what is the melting point. And in the case of glass transition temperature, at that temperature the polymer never melt. The polymer just becomes soft. Whereas in the case of melting point, it consider the temperature at which it melts. So again, the melting point is another one more property of the polymer. The third one is the solubility of the polymers, because the solubility or the phenomenon of movement of the solute molecule into a solvent system, that we call it as the process of solubility. In the case of solubility, if you administer a drug with the help of certain polymers, the polymer has to release the drug from the drug delivery system. Initially, the polymer is holding the drug molecule within it. Later, the polymer has to release the drug from the drug delivery system. For that, the polymer has to be solubilized. Once if it is solubilized only, it can releases the drug out from the delivery system. So these polymers are likely to be soluble in a specified liquid than are their low molecular weight analogues. The solubility of most polymer decreases as their molecular weight rises. As with mixture of low molecular weight liquids, the solubility of polymers often increases with rising the temperature. So here it states the solubility of this polymer depends upon the molecular weight of the polymers. And all the polymers are not soluble in water. It is having its own specific solvent system. Some polymers may be soluble in water, some may not be. Some may be soluble in the hexane, some may be soluble in the ethanol. Methanol depends upon the polymer. And this solubility varies based upon the monomer of the polymer. Secondly, it also based upon the molecular weight. So at higher the molecular weight, the chances for the less solubility. So this drug releasing mechanism is depends upon, as you learned, it also depends upon the swellability. That means the polymer is not solubilizing there, but it takes up the water and it swells. So that is another one more property, that the swellability, that it swells and releases, where it's not becoming becomes solubilized in the system. Next point is the crystallinity and amorphism. So these two things, that is crystalline nature as well as amorphous nature, you know. One is very rigid, other one is not that much rigid without a proper structure. So amorphous or glassy polymers do not generally display a sharp melting point. Instead, they soften over a wide temperature range. So these polymers do not exhibit a sharp melting point, whereas they become soft over a wide temperature ranges. Crystallinity, what is crystallinity? You know. So this defines the degree of long range order in a material and strongly affects its properties. The more crystalline a polymer, the more regularly aligned its chain. You know, it's having a rigid structure. So it is having a proper arrangement between the monomers. A proper arrangement between the monomers make these molecules more crystalline and more rigid in nature. Increasing the degree of crystallinity increases the hardness and density. So you know how this crystallinity which closest to the hardness as well as to the density. A polymer molecule structure strongly affects the crystallinity. If it is regular and orderly, highly symmetrical, it will pack into crystals more easily. In a way, the molecule wants to get next to each other in crystalline domains. If the molecular structure is not having a regular symmetrical, it won't. So, the entire crystallinity leads to the rigidity as well as the higher density of this molecule. Why it is becoming important? Because the more denser or more harder, lesser will be the release of the drug from this polymer. As in the case of the drug also, if we consider, the highly crystalline molecules will have less solubility. The same way the high crystalline polymers will also have the less solubility. So this crystallinity, why it becomes more crystalline? It is because of the proper and more rigid arrangements of the monomers in the polymer system. The polymer strength and stiffness increases with crystallinity. The polymer strength and stiffness increases with crystallinity as a result of the increased intermolecular interaction. This word you have to keep in mind. A result of increased intermolecular interactions, there is higher strength, stiffness for the polymers. With an increased crystallinity, the optical properties of the polymers are changed from transparent to opaque. That is, with increase in the optical properties of the polymers are changing from the transparent amorphous form to a semi-crystalline form. So, if the polymer is amorphous in nature, with the proper arrangement of monomers in the system, the amorphous form gets converted into an opaque or a semi-crystalline in nature. If the structure is linear, the polymer chain can pack together in regular arrays. So this is given with the example of polypropylene chain fit together in a way that the intermolecular attraction stabilizes the chain into regular lattice or crystalline state. With increased temperature, the crystal cells starts to melt and the whole polymer mass suddenly melts at a certain temperature above the melting temperature. The polymer molecules are in continuous motion and molecules can slip past one another. Now, the next one is the heat of fusion. The heat of fusion of a polymer given as delta H is essential thermal property of polymer which permits the degree of crystallinity to be obtained from thermal measurements. So the heat of fusion is a parameter which is used to measure the degrees of crystallinity. So how crystalline it is? It is being measured based upon the heat of fusion, that is delta HF. Again, the molecular weight. The polymer molecular weight reflects the number of entanglement of polymer chain in solution. Thus, solution viscosity, it has found that a lower molecular weight solution tend to form beads rather than fibers, and higher molecular weight solution helps to form fibers with a larger diameters. That is, the configuration or the entanglement of polymers depends upon the molecular weight. So if we make the solution of the polymers, the molecular weight, a low molecular weight solution tends to form beads. So beads, as you know, it's like a powder like or a separate unit structures, small spherical unit structures, we call it as the beads. So this low molecular weight polymers, once if we kept in the solution, once we made it as a solution, it will be present as a bead form, whereas the higher molecular weight being existed as a fibrous form. So when the polymer concentration is low, an adequate number of entanglements of polymer chain can ensure a sufficient level of solution viscosity to fabricate uniform fiber web during electrospinning and restrain the effect of surface tension. In other words, the higher molecular weights are not always essential for the electron spinning process if the intermolecular interactions are sufficient for the interchain connectivity obtained through chain entanglements. So this point is much important in the fabrication of the polymers. So in during the fabrication or during the development of the polymers, if the polymer concentration is less, if the polymer concentration is less, a sufficient number of entanglements of polymer chain may occur. This will provide the sufficient viscosity to fabricate the systems. So this polymer development or polymer fabrication by means of electron spinning mechanisms, the higher molecular weights are not essential for electron spinning process, whereas the lower molecular weight polymers is sufficient for electron spinning processes. Biocompatibility is another property and another characteristics of the polymer that encompasses many aspects of the material, including its physical, mechanical and chemical properties, as well as potential cytotoxic, mutagenic and allergic effects, so that no significant injuries or toxic effects on the biological functions of the cells and individual arises. So here it confirms that it's only the polymer should be compatible with our normal body. Again back to the viscosity. It's for again depends upon the molecular weight as we discussed. So higher molecular weight polymers greatly increases the viscosity of liquids in which they are dissolved. The increase in viscosity is caused by strong internal friction between the randomly coiled and swollen macromolecules. The increase in viscosity is caused by a strong internal friction between the randomly coiled and swollen macromolecules and the surrounding solvent molecules. How much a polymer increases the viscosity of a solvent will depend on both the nature of the polymer and the solvent. So the increase in viscosity or the viscosity may varies from solvent to solvent, from polymer to polymer. A same polymer that dissolves in different solvent system will gives you different viscosities. And it again depends upon the molecular weight of the polymers. And viscosity has a great impact in the drug release also. Thermal stability is defined as the ability of the polymer material to resist the action of heat and to maintain its properties such as strength, toughness or elasticity at a given temperature. The thermal stability of a polymer is usually determined by thermogravimetric analysis. The next one is heat conductivity or capacity. The extent to which the polymer acts as effective insulator against the flow of heat. So that is considered as the heat capacity. Thermal expansion. The extent to which the polymer expands or contracts when heated or cooled. The extent to which the polymer expands or contracts when heated or cooled is considered as the thermal expansion. Next one is permeability. The tendency of a polymer to pass extraneous materials is considered as the permeability. This we saw the permeability word we are regularly discussed in our biological system. Then elastic modulus, the force it takes to stretch the plastic in one direction, that is the elasticity. The tensile strength, the strength of the polymeric material. Then resilience, the ability of the polymer or the plastic to resist the abrasion and wear, we consider as the resilience. Refractive index, the extent to which the plastic affects the light as it passes through the polymer. The extent to which the plastic affects light as it passes through the polymer. So once the light passes the polymer, how much it can affect the permeability of this light is considered as the refractive index. Resistance to electrical current is a material an insulator like most polymers, or does it conduct an electrical current? This is what we are ensuring in the resistance to an electrical current. Okay, so that's the some of the properties of the polymers. Okay, thank you.